Hey there students, I've got a little video here to help you with the solutions to the practice test. It's likely to be a pretty long video, so if you're after a particular question, there's time codes in the description. Okay, the first question is looking at converting between index form, expanded form, and a value for particular expressions. So let's come up with just a different example. Say if we had 4 to the power 3, just as an example, we call for the base for this one, and then 3 is the index or the power for this one. And that pretty much, the 3 tells us how many times we're going to use 4 in the multiplication. So 4 to the power 3, for example, is 4 times 4 times 4. And I'm going to run out of space on my trackpad. That's okay. Okay, so for this one here, we've got 8, and we're using 8 4 times in that multiplication. So in index form, I'm going to write that as an 8 as the base, and to the power of 4. So my index is 4 for this one. On the right-hand side, I need to find out what the actual value is. So that's like, well, what's that as an actual number if we do that multiplication, if we work it out? And for this, I'm going to use my calculator. I'm going to say 8 to the power 4, which gives us 4,096. Now, on the actual test, you won't be able to use your computer, so your computer calculator won't be available. So you'll need to know how to do that function using your scientific calculator. Okay, 6 squared, that's 6 multiplied by 6. So I've got a base of 6, an index of 2, so I'm going to use 6 twice in the multiplication. That's going to give me a value of 36. And for the last one, 2 to the power something gives us 32. Well, 2 to the power 2 gives us 4, to the power 3 gives us 8, to the power 4 gives us 16, to the power 5 gives us 32. So that means that 2 multiplied by 2, multiplied by 2, multiplied by 2, multiplied by 2. So 2 times 2, 4, 8, 16, 32. And we write that in index form as 2 to the power 5. Lovely. Okay, question number 2. We need to use, for the first part, we need to use a little bit of what we know about the 0 index. So one of our index law properties is that anything to the power 0 is equal to 1. And the reason for that is if I say, for example, had 3 to the power 3 divided by 3 to the power 3. I'm jumping ahead using index law 2 here, but I hope that's okay. It means that what I'm essentially, if I use index law number 2, 3 take away 3 is 0. So that simplifies to 3 to the power 0. But another way to think about it is to say, well, in expanded form, I've got 3 multiplied by itself 3 times in both the numerator and the denominator. So all of these cancel off, 1, 1, 1, 1, 1, 1. And you'll notice that that will equal 1 because I'm essentially dividing 3 to the power 3 by itself. So 3 to the power 0 is the same as 1. And I could have picked any example for that. But that's an important property to remember, that if you've got anything raised to the power 0, the value of it is always going to be 1. That's pretty much the takeaway for this one. Okay, the second question, so 1 to the power negative 3. So the thing to understand here is if you've got any base raised to a negative power, we can rewrite that as 1 over the same base raised to a positive power. So that's another property that's important to know. The reason that this works is if we say had 3 to the power 2 divided by 3 to the power 5, let's say. Using index law number 2, we'd say, well, 2 take away 5 gives us 3 to the power negative 3. But again, if I write this out in an expanded version, just to demonstrate it, 3 times 3 times 3, 4, 5. I'm going over a little bit, but that's okay. Again, we can cancel off a couple of these, and we still have 3 to the power 3 in the denominator and 1 multiplied by 1 in the numerator, which is 3. So I've got 1 over 3 cubed. So what I've shown there is, well, hopefully is what I've explained, is 3 to the power negative 3 is the same as 1 over 3 to the power positive 3. So again, that's why it works, but this is the property that you actually need to know. If you've got something raised to a negative power, we make the power positive and put it in the denominator. So for this one, 1 to the power negative 3, I'm going to rewrite that as 1 over 1 to the power positive 3, which 1 to the power 3 is still 1 because 1 times 1 times 1 is still 1. So my actual value for that, after all that, is just going to be a 1 for this one. But these mechanics of why it works are going to be important for future questions. Okay, question number 3, using index laws. All right, the first 3 aren't too bad. Index law number 1 is if we have the same base raised to, and we're multiplying it, well, sorry, a base raised to a particular power, and we multiply that by the same base raised to a different power, we can simplify those powers by adding them together. The reason for that is we've got n to the power 5, so n times n times n times n times n, times n to the power 1, so 1 more n just there, and then n to the power 6, so times n times n times n, another 6 times. So if we've got n multiplied by itself all of those times in a row, we can simplify those powers by just adding them together. So n to the power 5 plus 1 plus 6, which is 12 for that one. So again, that's just one of the index laws you've got to, I say you have to know, it's more that you have to know how to use it because these will be written on the board. Okay, index law number 2 is similar, but it deals with division. So when we have the same base and we are dividing, we can simplify the powers by subtracting them. So for this one, we've got 5 to the power 13 divided by 5 to the power 5. I'll subtract those powers, which leaves me with 8. Okay, similar sort of thing for that one. If we had, say, 3 to the power 5 divided by 3 to the power 2, if we expanded that, and I've not left myself a lot of room, but that's okay. If I expanded this, I could then cancel off a couple of pairs of this, leaves me with 3 to the power 3 in the numerator, which is the same as 5 take away 2. Okay, next one we've got is index law number 3, where if we have something raised to a particular power and then the whole bracket is raised to another power, we can simplify those by multiplying. So in this case, we've got b to the power 4 raised to the power 4. We want that to be b to the power 4 times 4, which is b to the power 16. So again, that's using another index law for this one. Okay, this last one is actually a little bit tricky. It's not too bad. What I'm going to do for this is start off by using that third index law just on this part of the expression here. So I've got to square the whole thing. So 3 to the power 2 is 9. And p to the power 2 is p to the power 2. And now I can carry on by writing the rest of the expression. So q to the power 5, 3p to the power 3. I'm just copying this out, by the way. I've just got rid of the bracket that was there. 18p to the power 4 times q to the power 6. Okay, this looks complicated, but really you've just got to do one thing at a time and kind of whittle it down until you get one answer. All right, the first thing I'm going to deal with is my numerals for this one. So I've got 9 times 3 in the numerator, and I'm dividing the whole thing by 18. What I'm going to do first is say, well, 9 divided by 18 gives me 1 over 2. If that was a regular fraction, that would simplify to 1 over 2. And now in the numerator, I've got 1 multiplied by 3, which will give me 3. And in the denominator, I've got that 2 that I cancelled earlier. So no matter what, in my final answer, it's going to be 3 something over 2. Now I'll go ahead and simplify my p's. So I've got these ones to contend with in these spots here. All right, so in the numerator, p to the power 2 times p to the power 3. Using index law number 1, that gives me, I'm not going to scribble that actually, I'm just going to give that a neat cross out. Gives me p to the power 5 by adding them together. But now I can cancel p to the power 5 in the numerator with p to the power 4 in the denominator, which is just going to leave me with p to the power 1, which I'll write as 3p. Now I can deal with the q's. Okay. Similar story for this one, q to the power 5 in the numerator, q to the power 6 in the denominator. That just cancels down to q to the power 1 in the denominator, like that. So your final answer for this one is 3p over 2q. The next question is kind of similar. I've got to start by getting rid of the whole bracket. I think index law number 4, or it could be number 5. I think it's number 4 though. If we've got a fraction in a bracket like this, and we raise it to, get my letters right, and raise it to another power, we just raise everything in the numerator to that power and everything in the denominator to that power as well. So I'll start off with this one. 6 squared is 36. X to the power 3 times 2 is x to the power 6. And that's over 3 squared, which is 9. And then x will become squared because 1 times 2 is 2. And then same thing for y as well. And now I can have a little bit of a cancel party. 36 divided by 9 is 4. So that cancels to 4. X to the power 6 divided by x to the power 2 gives me x to the power 4. And I'm left with y to the power 2 in the denominator. Happy days. So those last two are a little bit harder and are worth more marks. But bear in mind that you'll have questions similar to the first 3 on the paper as well. And I'm sure you'll agree that they are quite accessible. Okay, question number 4. State the value of 2 to the power negative 2. So we're going to recall what we learned in question 2 and say anything raised to a negative power, we'll write that as 1 over the same base raised to a positive power. So I'm going to start by rewriting this as a fraction with positive indices. So that's going to be 1 over 2 to the power, not negative 2, but positive 2. Which is 1 over 2 squared. I'm going to write that as 1 over 2 to the power 2, which is 4. And then as a decimal, I'm sure you'll know that's 0.25. Happy days. Okay, let's do, next we've got another question that involves negative indices. So first I'm going to use index law number 1 to simplify the first part of the question. So k to the power negative 1 multiplied by k to the power negative 7. It's, hang on a sec, I've not made my negative 1 very clear, and it will annoy me. K to the power negative 1 multiplied by k to the power negative 7. Cool. All right, so I'm multiplying those bases. I'm going to add the powers together, which is going to give me k to the power negative 8. And I'll rewrite that as a fraction with positive indices. K to the power negative 8 is the same as 1 over k to the power positive 8. So that's not too bad. Quite accessible. The next one is slightly harder. There's a number of different ways that you can go about doing this. What I'd probably consider, I'm just going to rewrite this to begin with actually, because then I can have a cancel party and show it a little bit more clearly. F cubed g squared over 21e f to the power 4 g. Okay, we've obviously got a little bit of a cancel party on our hands here, which is fine. Okay, so I've got 7 divided by 21 to begin with. So 7 over 21 cancels to 1 over 3. So my fraction is going to be something over 3. It's going to involve that. Okay, now I'm going to cancel. What do I want to cancel first? I'll get rid of this. What I might do is get rid of this e to the power negative 5. And you could write it if you wanted to at the end, I suppose. You can make it positive and just plonk it over here. So e to the power positive 5. And then just combine e to the power 1 and e to the power 5. So using index law 1, we can add those together to give us e to the power 6, because 5 plus 1 is 6. So I've got e to the power 6 in my answer just there. F to the power 3 divided by f to the power 4 gives me f to the power 1 in the denominator. So just f there. And then we've got g to the power 2 divided by g, which will just give me g to the power 1 in the numerator. So there's a bit more going on with that one. But again, there's a few different steps there and a few marks awarded for each step. Oh, well, there's 2. But there'll be, if you get some of it right, you can at least do a little bit of cancelling or make some of the powers positive. There'll be some marks thrown in there for you. Okay, I think mercifully that might be the end of index laws. Not for the rest of your life, but for this video. Okay, the next question is writing the following numbers in scientific notation. So for scientific notation, we want a number that's between 1 and 10, but greater than or equal to 1, but less than 10. So let's say 2.37 would be that number for our first question. And now we want to multiply it by whatever power of 10 is going to make it into the number that we started with. So here we've got 237,000. So to multiply that by a number to give us, to multiply 2.37 to give you 237,000, we're going to have to multiply that by 10 to the power 5. One way you can kind of check this is see how many decimal points you would have shifted from here to get from 2.7 to 237,000, which is 1, 2, 3, 4, 5. For me, I'm more comfortable remembering some of the, I guess, key shortcuts, where 10 to the power 3 equals 1,000, 10 to the power 6 is 1,000,000, 10 to the power 9 is 1,000,000,000, and so on. So because I've got 237,000, I know it had to be 10 to the power 5 because it's a magnitude, order of magnitude less than 1 million for that one. Anyway, so 8.5 million, our number between 1 and 10 is 8.5. And then I multiply that by 10 to the power 6 to make it into 1,000,000. The next one's a little different. We've got a negative power for this one. So we still start with a digit, or number rather, between 1 and 10. So 3.265. Now, this is a pretty small number, but we've moved our decimal point 1, 2, 3, 4, 5, 6 places. So that's going to be multiplying it by 10 to the power negative 6 for this one. So yeah, so that little how many decimal places it shifted isn't the best mathematical way to think about it, but if you're in a tight spot in the test, that's one quick way that you can determine how much you need to or what power of 10 you need to multiply by. Similar story with this one here. So 10 to the power 7 is in the tens of millions. If 10 to the power 6 is millions, then 10 to the power 7 is tens of millions. So we can rewrite that as 51,000, so 51 million rather, 730,000, and we'll fill in the rest just there. One thing you could do as well is if you wanted to use your calculators just to double check, you could say 5.173 multiplied by 10 to the power 7, which will give you the same, hang on, that didn't quite give me the same thing. Maybe I'll write it slightly differently. So this is why it's important to know how your specific calculator works. 173 times 10 to the power, oh, sorry, no, I know what it's doing. 5.173 times 10 to, and I'll just use my power button instead, 7. Okay, another good reason why it's a good idea to figure out how your calculator works in advance of the test happening, but that's okay. And similarly, we've got to convert this to a small number. So this is going to be 0.000108. And similarly, if I started from here, my decimal point has shifted 4 spaces across like that. 1, 2, 3, 4. So again, I think of 10 to the power negative 3 as, again, you can have like your little shortcuts thrown in there as well, but that's just one way that you might like to do that one. Okay, this next one does combination calculations. So what we're looking for here is the skill involved, I guess, is to rewrite it in such a way that you can make the problem a little easier to solve. So we've got 3 times 10 to the power 8. So that's 30 million or 300 million. Yeah, 300 million times 2.4 times 10 to the power 4. I'm going to rewrite that as 3 times 2.4 times 10 to the power 8 times 10 to the power 4. Okay, 3 times 2.4 is easy enough to do. That would be 7.2. And that's multiplied by, and then 10 to the power 8 times 10 to the power 4. I'll use index laws to help simplify that. 8 plus 4 gives me 12. So if I'd got, say, 72 times 10 to the power 12, I'd have to make it 7.2 and then increase the power slightly. But as it happened, our answer, the numeral in our answer was between 1 and 10, so that was quite merciful in some ways. And similarly for the next one, we can do a little bit of a combination type thing where we've got 3.3 times 10 to the power 5, and that's being divided by 1.1 times 10 to the power 4. So what I'm going to do for this one is say, well, 3.3 divided by 1.1 is 3, so 3. And 10 to the power 5 divided by 10 to the power 4 is 10 to the power 1. So that simplifies to 3 times 10 to the power 1. For that one, you'd be tempted to write 30, but remember that the answer must be in scientific notation. So that number that we've got at the front has to be between 1 and 10. So if it's asking for scientific notation, make sure you leave it as such. Okay, simple interest. So now we've got a bit of a change in topic. Now, simple interest is given by interest is equal to the principal, which is just a way of saying the amount that we start with, multiplied by the interest rate as a decimal. And the interest rate, if you're given it as a percentage, just divide that by 100 and you'll get the rate for that one. And then we multiply that by the time that the loan or investment or whatever it is runs for. So here we've got how much interest would she earn in a year. Our mystery protagonist, they're going to earn, let's see, so we've got principal, which is 4,300, times the rate, which as a decimal is 0.05, and then multiplying that by the time. In the question it says how much interest will she earn in 1 year, so 4,300 times 0.05, 4,300. I could really do that in my head, but it's late and my kids are asleep, and I think I'm just going to leave it at that. $215 for that one. Okay. For part B, it's asking how much money will be in the account at the end of the 5 years. There's actually 2 parts to this. So we're going to figure out the simple interest, which will be given by $4,300 multiplied by 0.05. And multiply that by 5. So we can go 215 effectively times 5 for this one. So I'm going to use our first answer, which is $1,075. Now we've got to do something a little bit different as well. So we've got, the question's actually asking how much money is in the savings account in total at the end of the 5 years. So to find the final amount, I've got to take the principal, so the amount that we started with, and then add on any interest that was earned. So in this case, the final amount that's going to be in the account, we're going to have the 4,300 that we started with, and we're going to add on the 1,075 that was made in interest, which will give us a nice total of 5,300. Let's write my dollar sign. $5,375. Because I've got a few different numbers written here, I might just put a highlight through that or similar to. This is good practice for every question actually, but if you can make it clear what your final answer is, that's a wise thing to do. Next one, Noah is saving to buy a car. He has invested some money for 6 months. Okay. This is another how much money will be in an account at the end question. So we've got to find the interest and the amount separately. So the interest this time, we start off with 7,800. The interest rate is 16% per annum. So divide 16 by 100, 0.16. That is a really high interest rate. They're very lucky. And but the time for this one is 6 months. What's important is that your time units have to be the same as whatever the rate units are in. So 16% per annum means 16% per year. So I'm going to change 6 months to years, which is 0.5 years because it's half of a year. So my interest there on my calculator again, 7,800 multiply by 0.16, multiply that by 0.5. Gives me $624. But again, this question's asking for the final amount. So the final amount is going to be given by what I started with, which is 7,800, and I need to add on to that $624 dollars. So for this one, we're going to end up with $8,424. And just in case I've had a mental blank and I've got that wrong, I'm going to double check, because otherwise, yeah, cool. Silly. You got to check. It's important to check. And that's my final answer. I've got a lot of numbers written on that, so I'm going to make it clear that that's my answer. All right. The next question, we've got to do the inverse. So we've talked already about interest being principal times rate times time. We can rearrange this any way we like if we wanted to find the principal, the rate, or the time. In this question, we've got to find out the amount that was invested, which is the principal. So if I divide both sides by RT, I can cancel those off, which will leave me with principal equals interest divided by rate times time. What's quite helpful to visualize here can be like a little triangle thingy. So R over P RT, like this. So what you can do, it's on a little bit of an angle, I apologize for that. But essentially what you can do is, if you're calculating the interest, can cover it up and it's leaving you with principal times rate times time. If you're figuring out the principal like we are, leaves you with I over RT, so interest divided by rate times time. If you're finding out the time, for example, it would be interest divided by principal times rate. So it's just a handy little shortcut that you can use to help you figure out what the formula is. Anyway, so the principal is going to be given by the interest earned, which is 5,300, divided by the interest rate, so 4.2 divided by 100, 0.042, and multiplying that by 6 for the 6 years. This is where you've got to be a little bit careful with brackets as well. So I'm going to do 5,300 divided by bracket 0.042 times 6. Otherwise, your calculator's not going to figure that out correctly. It's going to think that your times 6 is up here instead, which it isn't. The other thing you can do is just divide it by 6 and not use brackets, but I probably use brackets and keep it as a multiplication if it was me. Anyway, so our initial amount invested was $21,031. Because we're dealing with money, I'm going to round this to 2 decimal places. So 0.75 for that one, because my digit after the second decimal place is 5 or greater. 6 is 5 or greater. So I'm going to round it up from a 4 to a 5. Beauty. Happy days. Okay, I'm just going to have a quick look at what's next. Oh, travel graphs. Very exciting. Okay, so travel graphs show distance against time. I'm going to have to do a little bit of scrolling up and down for this one. I hope it's okay. It kind of has to be, so whatever. So this graph is showing Tom's distance from home and how that varies with time when he visits his friend Ian. Okay, so just to go over what's actually happening here on the graph. Notice here that we're going, time is 0 and distance is 0. As we go along here, the distance from his home is increasing, but the time is increasing as well. So it takes this guy 20 minutes to travel 1,000 meters. He then spends 10 minutes stationary, and we know he's stationary because the distance doesn't change. And then he starts moving again. Then he's stationary for a pretty long period of time. I'm going to assume that's when he's at his friend Ian's house. And then he starts moving again, but this time the distance to home is decreasing, which means that he is returning home. Okay, I'll get rid of all of my highlights. Okay, question A, 12A. How long does Tom spend at Ian's? Okay, we're going to read, I'm going to assume that it's this long stay here and not the shorter one over there. So how long does Tom stay at Ian's? He's there from 40 minutes into the journey until 90 minutes into the journey, which is a difference of 50. So 50 minutes for that one. How far is it from Tom's to Ian's? Well, if we read off the graph this way, he arrives at Ian's house when he's 3,000 meters away from home. So the distance is 3,000 meters. Cool. For how long does Tom stop on the way to Ian's? Oh, cool. That's explained further down. So we've talked about this already, but he stops here. Difference between the start and the finish is 10 minutes. It goes from 20 to 30. So he stops for 10 minutes. On what part of the journey does Tom travel the fastest, and how can you tell? Okay, this is where we start to talk about gradients. So if you just follow me with this for a moment, as he starts here at home and gets to this point here where he stops, he travels a particular distance, 1,000 meters, and he does that in 20 minutes. Here, he travels another 2,000 meters, and he does that in 10 minutes. And looking at the end just here, he travels 3,000 meters in 30 minutes. Okay. Now, you could work out the speed for each section of the graph here, but you actually don't have to do that. What you can do instead is look at what has the steepest gradient, because the gradient is the steepest between two particular points. It means that he's covering more distance in the time that's available. So without even figuring out what the speed is, if we just look for what the steepest gradient is, that will tell us when he was going the fastest. So here we've got a gradient of, was going 1 unit, or 1 on the grid at least. We're going 1 across and 4 units up. That's steeper than what we've got on the left-hand side. On the right-hand side, we go 1 unit across and 2 units down. So the steepest gradient is gonna be before he gets to Ian's, but after he's actually stopped. So 2 marks for this question. So what part of the journey does he travel the fastest? After he stops, because it is out, you've got that differentiates between the two. After he stops on the way to Ian's, so he's traveling towards Ian's house, but it's the time after he stops. You could say the gradient is steepest during this time. Gradient is the steepest. And again, it's not asking what the speed is. It's just asking where is he going fastest. So you don't have to do any more calculations. No, we do though. So average speed at which Tom travels on his way to Ian's. Okay, so that's from here, from 0, 0, all the way up to here. So we've covered there 3,000 meters. Hang on a sec. So average speed. And we're asked to find it in meters per minute. So speed is given by distance divided by time. So for this question, we're going to take the distance, which is 3,000 meters, divide it by the number of minutes that it took, which was 40. Oh, I don't like going horizontal with my equals, but I don't think I have much of a choice here. 3,000 divided by 40 should give you 75 meters per minute. Okay, and now we're going to change that to meters per second. So what we want to do for this one, if we're traveling 75 meters per minute, if there's 60 seconds in a minute, we'll have to convert that by dividing by 100. So 75 meters per minute. If we divide that by 60, gives us 1.25 meters per second. Beautiful. I think we're on the home stretch now. This might be the last page. Oh, woohoo. Okay, there's 2 formulas that we need for cylinders. One is for volume. So you might recall doing prisms in year 8. The way we find the volume of a prism is to take the surface area of the cross-section and multiply it by the height. For cylinders, it's really, really similar, but the area of the cross-section is given by pi times the radius squared, and we multiply that by the height of the shape. The height's not always literally how tall it is, by the way. It's just whatever direction that cross-section is going in. So for this, if I'm going volume, I'll start by writing my equation. Volume is pi r squared times the height, which for this shape, we're mercifully given the radius, pi times 7 squared times 22. And again, on your calculator, it will be important to know where, it was clear all. It will be important for you to know where pi is. And again, you can't use your computer for this one. You have to use a scientific calculator. Okay, so that gives me a result of 3,386. And I'm rounding to 2 decimal places, 0.64. And my units are millimeters cubed because it's volume. Okay, the next little part that we've got here is the surface area. Surface area is a little bit more complicated, but once you understand where it comes from, it's pretty much just a case of plugging in the formula. What I'm just going to draw here, that curved surface that's in the middle, if we unfolded that, we're basically going to get a rectangle. So the net is going to look something a little bit like this. We've got a couple of circles, one on each end. Might draw it like this actually. A couple of circles and a rectangle in the middle. So the surface area formula basically comes from this. We've got 2 lots of pi r squared. Because we've got pi r squared gives us the area of a circle, and we've got 2 of them, so times 2. But it's a little bit trickier as the curved surface. What you've got to imagine here is that this rectangle has got a width. The base width is going to be the same as the circumference of the circle, so 2 pi r. And the height of it is just going to be the height of whatever the height of the cylinder is. So if we think of, well, what's the area of that rectangle? It's going to be 2 times pi times the radius, because that's the length of the whole base. And I'm going to multiply that by the height of the shape. And that's it. So it's tricky to get your head around, and the formula looks kind of scary because there's a lot going on with it. But again, it'll be written on the board during the test, and as long as you can identify what the radius and the height are, you shouldn't really have too many dramas as long as you are comfortable plugging this into your calculator. So again, surface area is 2 pi r squared plus 2 pi r h. Okay, 2 times pi times the radius squared, which is 7 squared, plus 2 times pi times 7 times the height, which is 22. And again, I'll get my trusty calculator. 2 times pi times 49 plus 2 times pi times 7 times 22. Which looks to me like it's 1,275. I'm rounding to 2 decimal places, 0.49, and my units are millimeters squared for this one. Cool. Oh, last question. That's so exciting. Okay, we've got 2 shapes here. We've got a triangle and we've got a semicircle. So to find the area of this shape, we've got to do 2 things. We've got to find the area of shape 1 and add it to the area of shape 2. Okay, so for a triangle, our area formula is base times height divided by 2. For a circle, it's pi times the radius squared. But because we have a semicircle, we're going to divide it by 2 as well. Okay, then we're going to pick out the right information from the question. So don't forget that for a triangle, we've got a base length of 6 just here, but we're looking for the perpendicular height. We need the height that's at the right angle to the base. So we're going to do for this one 6 multiplied by 4, which we divide by 2. And we're going to add onto that pi times the radius squared. So pi times, and don't forget the radius, we're given the diameter for this question. So the radius is going to be half of that, which is 3. So pi times 3 squared, and I'm going to divide all of that by 2. Okay, lovely. I'm going to do a little bit of cancelling there. That's 12. That makes the calculator's job slightly easier. 12 plus pi times 3 squared, which is 9, divided by 2. And that has spat out for me 26.1. What are my units? Meters squared for this one. Okay, if you watch this the whole way through, congratulations, you get a prize, and the prize is my respect. Thanks for watching.